Good morning. In this section, we're going to keep on the path to finding global maxima and minima in the setting of applications. Last time we looked at local maxima, local minima. Now we're going to talk about absolute maxima and absolute minima. So let's look at an example. So I'm going to just draw a picture of a function. And this function is going to be only defined on a certain interval. So we've got points A, x1, x2, x3, x4, and B. A and B are the endpoints. Again, our function is stopping at those endpoints. And I want us to find the local maxima, the local minima, the global max, and the global min. So global max, global min, as a review from pre-calc, they're also called absolute max, absolute min. That's just the overall largest and smallest values for the function. So this is actually a pre-calc question, so please pause the video, see if you can find all of the local max, local min, global max, and global min. All right, hopefully you gave that a shot. So we have local max and the local maxima. So these are the points that, if you just look close, they're the highest points. So that would be A, that's a high point, x2, that's a high point, and x4. So A, x2, and x4. Local minima are locally low points. So, for example, x1, that's a local low point, x3, and B, that's a local low point. Absolute max, absolute or global max, and that's just the highest point that we see. That would be at A. And the absolute or global minimum is the lowest point that we see. It looks like it's x1. So let's note that the global max is one of the local max. The global min is one of the global min. So it sounds like we can look for our local max, local min, and then find the lowest of those to get the global. Look at the local max. Find the highest of those to get the global max. Look at the local min, find the lowest of those to find the global min. So that seems like the recipe. Okay, so we can compare all of our local max to get the global max. Again, we'll get the highest of those, and we can compare the local min to get the global min. We could just use the lowest of those. Let me also say that on this closed interval, the critical points from last time would help us find these local max. In fact, that would have helped us find x1. X1, for example, that's a critical point, and x3. However, B, not so much, because if our function kept continuing this way, and I'm just interested from A to B, B would not have popped up as a critical point, right? Because the function keeps going. So on these closed intervals, it looks like we not only have to look at the local max and local min, we also have to check out the y coordinates of the endpoints, because we may have missed them when we were doing the critical point computation. So compare local max, let me say, endpoints slash endpoints slash. And this is the scenario when we're looking at a closed interval. So so in summary then, if f is continuous on AB, that is the closed interval AB, compare local max and min and endpoints to get global max and min. So I'm kind of stating this. If f of x is continuous, then you do this process. So a good question then is, will we always get a global max and min if f of x is continuous on the closed interval? Well, we don't have enough tools to prove that, whether we will or not, but I want you to use your imagination and imagine having a string that you can kind of move up and down. So that's our continuous function. And it's on a closed interval. Question, will there always be a highest point or highest value and a lowest value? The answer is yes, there will. One thing that some students creatively come up with is they say, well, wait a minute, what if my string looks like this? You know, let's say it's straight. Sorry, it's hard to make it straight with the camera. Horizontal line. Well, in that case, our function still has a global maximum of some value, maybe 10, and that value happens to be the same thing as the global minimum. So it still does have a global max and a global min. So if f is continuous on the closed interval, then we are guaranteed to have a global max or global min. Well, this then begs the question, what if f of x is not continuous? Or what if the interval itself is not closed? Will we always get a max and min? Let's check that out. So let's say it's not continuous. What if we have an open interval? Well, it turns out that if our function is not continuous on the interval, it doesn't have to have a global max or min. If we have an open interval, it doesn't have to have a global max or min. So pause the video, try to come up with a function that's not continuous, that has no global max or min, and then do the same thing for a function on some open interval that is continuous. Try to come up with an example which doesn't have a global max or min. All right, hopefully you pause the video. Not continuous. How about this guy? I feel like we saw this in a previous lecture. This guy does not have a maximum. It's not continuous, does not have a maximum. Another example. How about this guy here? This one, not continuous. Got to have a vertical asymptote. Happens to not have a maximum or a minimum. So what about on the open interval? Well, how about something really boring like the cube function? So the open interval I'm looking at here is negative infinity to infinity. This guy has neither a global max or a global min. A function that's a little bit tamer is maybe the quadratic function. This guy has a global minimum, but it has no global max. So the bottom line is that if you're on a closed interval and the function is continuous, you know you're going to get an answer. However, if it's not continuous or if it's the open interval, you're going to have to study it a little bit further because you may or may not have a global max or global min. Now, in terms of applications, most of the scenarios you're going to be studying, so it's going to be the one that we're going to be focusing on, is this open interval. And in particular, we're going to be looking at the negative infinity to infinity problem, or at least one of the infinities. And what we're going to do in this case is we're going to study the end behavior. You'll see what I mean exactly what this is all about in the example. But the idea is we're going to just take the limit or look at the function as x approaches infinity and see what happens. See if the function blows up or not. So let's see these concepts then put together in an example. So we want to find the global max of f of x equals x cubed minus 9x squared on the interval 0 to 10 and the interval -3 to infinity. So I'm guaranteed to get a global max here because this is a closed interval. This is a continuous function. This guy is not a closed interval. It's open on the right. So I might have a global max and I might not. Regardless, the steps for the first one are going to be first to find the local max, local min. So I'll take the derivative, 3x squared minus 9x. And let me factor out the 3x here. This guy's always defined. It's just a square function. So let me set it equal to 0. And it looks like 0 and 3. 0 and 3 are the places where that derivative is 0. So plugging in numbers, let me plug a million in, I get positive, positive. Let me plug in 1 in, I get positive, negative. Let me plug in -20 in, I get negative, negative. Okay, so it looks like this function, on the interval, and I mean, if you think about it, I'm really just interested from 0 to 10. I don't even care about this. This function is decreasing, then increasing. This function is decreasing, then increasing. Well, if I were asked to find the global minimum, then that would be a piece of cake because this guy has a local minimum at 3, and it's only got one local minimum. It's decreasing, then increasing. Well, if it just has one local minimum, that means that the endpoints are higher than that. This has got to be the location of the global minimum. But I'm not interested in that. I want the global max. Well, since I want the global max, I have more work to do because my function could either decrease, then increase like this, in which case this would be the global max, or it could go like this, in which case this would be my global max. I don't know. So I need to plug these guys into the original function. So we need to compute f of 0 and f of 10. Okay, so f of 0 is just 0 cubed minus 0, which is 0. F of 10 is 10 cubed minus 9 times 10 squared. Well, we can work this out in a second, or let me just say that 9 is less than 10. So this is 10 cubed minus something that's less than 10 cubed. So this is definitely bigger than 0. Or 100. It's going to equal 100. Because this guy is bigger than this guy, find the global max. The global max will occur at x equals 10. So that means we're in the case where my function's increasing as I go further out. Okay, well, let's take a look from -3 to infinity. From -3 to infinity. So now, let me get rid of this 10. Now now we're in this situation. Well, so our function continues to increase. It continues to increase. So there are two ways we can think about this. So our function increases, decreases, increases. So the only hope of any sort of maximum occurring would be here. But we just saw that at 10, the function f of x is higher than it is here. So it can't be here. And in fact, another way you could think about it is if you take the limit as x goes to infinity of x cubed minus 9x squared, we can now study the end behavior and see that this thing is going to explode to infinity. Because a cubic function dominates a square function, it blows up to infinity way faster. This limit is infinity. So what is the global maximum on this interval? Answer, there is no global max. So here again, we study the end behavior because we didn't have a closed interval. We weren't guaranteed to actually have a global max. So in summary, in this section, we looked to see how we could actually find global max and global min. We saw that if we were in the world of a continuous function on a closed interval, we're good to go. We know we're going to find a global max and a global min. If, however, the function is not continuous, which, quite frankly, is going to be minimally seen around here, or if we're looking at an open interval, okay, this we will be studying, then maybe it has a max, maybe it doesn't have a max. Maybe it has a min, maybe it doesn't have a min. You have to do the sign chart to see what's going on, and you have to then take a look at the end behavior. In the next lecture, which is the final lecture in this 3-lecture series, we're going to put all this stuff together in a word problem setting. So we're going to look at applications with this. So thanks for listening. Hope you enjoyed it, and I will see you next time.